Okay, um, hi doctor. So I'm Waha here. So today I'll be doing an in-depth analysis of promising beyond CMOS device, the negative capacitance field effect transistor. This work builds directly on my earlier research into the fundamental limits of MOSFET scaling. My analysis is grounded in two key papers published between 2020 and 2025, a device and technology roadmap perspective by Khan and data in Nature Electronics, and material physics perspective by Hoffman, and also ecologic in APL materials. Over the next roughly 30 minutes, I will cover the device structure, its operating principle, fabrication, performance, and future prospects. So let's go to the next slide. So here's the roadmap for today. I will follow the 6 required areas. So let me start with the motivation over here. So as I found in my earlier research, conventional MOSFET are limited by Boltzmann tyranny. The subthreshold swing cannot go below 60 milliwatts, but decays at room temperature. That hard floor is what prevents us from lowering the supply voltage further, and it's the root of the crisis in modern chips. So the NCFET attacks this directly by inserting a thin ferroelectric layer into gate stack. It creates an internal voltage amplification that allows switching below 60 milliwatts by decade. On the right are my two source paper A by Khan, which is like related to Nature Electronics, give the device and technology roadmap. Paper B will be Hoffman's and Mikologic provide the material physics foundation. Together, they let me synthesize both what and why of this particular technology. So structurally, the NCFET is remarkably close to a normal transistor, and that's a big part of its appeal. On the left, we can see like panel A shows a conventional MOSFET, silicon channel, source and drain, a thin interfacial oxide, and a metal gate. Panel B over here is NCFET. The only fundamental change is the insertion of thin ferroelectric layer, typically hafnium zirconium oxide, or we also can call it as HZO, between the interfacial oxide and the metal gate. So the gate stack now has the ferroelectric capacitor in series with normal MOS capacitor. That series arrangement listed in the key component on the right is the entire trick, and it's why NCFETs are considered CMOS compatible rather than considered as exotic. So let's go to the next slide. So now the heart of the physics, and where paper B is especially very useful. Ferroelectric materials store energy in a characteristic double well shape shown in panel A. The two minima are its own stable polarization states, but look at the region between the wells. Shades here, the energy curves are downward, meaning the second derivative of energy with respect to polarization is negative. In capacitor terms, a negative curvature of energy corresponds to a negative capacitance. When it's go to like panel B, shows the same thing as the famous S-shaped polarization, which is like a field curve. The highlighted middle branch have a negative slope, and that is the negative capacitance region. On its own, this state is unstable. The ferroelectric would just snap to one of the wells. The key insight, which I'll show next, is the placing it in series with the transistor's own capacitor stabilizes this negative capacitance state and puts it to work. So let's go to the next slide. Okay, so how does the negative capacitance actually help switching? This of the gate stacked as two capacitor in series, the ferroelectric now acting as negative capacitor on top of the transistor, normally channel capacitor CMOS. When you solve the series network, you get a voltage amplification factor. A greater than 1 shown in the top box. In plain term, like the ferroelectric internally boosts the gate voltage, so the surface potential at the channel rises faster than the voltage you actually apply. Recall from my earlier work that the sub-threshold swing equal the thermal term times the body factor M. The body factor is normally greater than 1. Here's the internal amplification pushes M below 1, and the moment M is less than 1, the swing drops below 60 milliwatts per decade. Particularly, that means like you reach the same on current at lower voltage, which is exactly where the power saving comes from. So let's go to the next slide. This slide shows the payoff visually. The red curve is like conventional MOSFET. The navy curve is the NCFET. The NCFET turns on far more abruptly. Its slope is steeper than the gray 60 milliwatt per decade reference line, which no conventional device can beat. Why does this matter so much? So we can say that like two ways to use it. Either you can get much larger on-off ratio within the same voltage window between switching, or you can keep the same performing but slide the low curve to a lower supply voltage and become dynamic power scales with the square of the supply voltage. Even a modest voltage reduction yields a large energy saving. This steep slope, low power promise is like exactly the point on which both of paper converge. So let's go to the next slide. So on fabrication, the great advantage of the modern NCFET is that it doesn't require exotic processing. The flow shows across the top is like essentially a standard transistor process with two extra consideration after forming the thin interfacial oxide. The ferroelectric HZO is deposited by atomic layer deposition to just 5 to 10 nanometer. Titanium nitrate metal gate capsid. Then comes the single most critical step, a rapid thermal anneal at around 4 to 500 degrees. As paper B emphasized, HZO is only ferroelectric in a specific crystal structure, the non-centrosymmetric atomic phase, and that phase has the coaxed into existence by capping stress and the thermal budget during this anneal. Get it right and you must have negative capacitance. Get it wrong and you just have an ordinary dielectric. Finally, source, drain and contacts are formed conventionally. and the whole stack integrates into FinFET or gate-all-around platform. So let's go to the next slide. So let's turn to the numbers, starting the headline figure of merit, sub-threshold swing. The chart benchmark the 60 millivolt per decade thermal limit against typical and best reported NCFET value. The key result and the whole reason this device exists is the experimental NCFET have demonstrated a minimum swing below 60 milliwatts per decade, which is simply impossible for any conventional MOSFET. That's the big call out on the right. I do want to be intellectually honest about two caveats that both papers raise. First, the steep swing is often achieved only over a limited current range, not across the full curve. Second, for logic application, the ferroelectric hysteresis has to be minimized, and that create genuine design tension. I used representative value from the published range here. The exact figure should be read from the exact specific papers. So next slide here is like broadening out the full set of figure of merit. The slide benchmark that NCFET against a conventional MOSFET. The chart on the left compares them across 4 axes on off ratio, drive current, switching energy, and sub-threshold swing. In normalized term, the table on the right summarizes the trade-off cleanly. On the winning side, sub 60 swing, a lower usable supply voltage comparable or better on off ratio, and lower switching energy, or while remaining Swiss compatible thanks to like HZO. On the cost side, there's one honest negative hysteresis, and the associated reliability and endurance concern must be actively managed, whereas the MOSFET has none. So the overall story over here is like which both paper agrees on is a clear engineering trait. You accept a manageable ferroelectric reliability challenge in exchange for fundamental physics level power advantage. So next slide. Before concluding, I want to explicitly address synthesis, how my two papers work together rather than just sitting side by side. They deliberately complementary. Paper A from Khan and Data and takes the top-down devices and roadmap view. It positions the NCFET and its cousin FET within the wider landscape of logic and memory, spell out the application level benefit, and argue the HZO finally makes ferroelectric devices manufacturable at scale. Its strength is the most what and where. Paper B, where Hoffman and Mikologic takes the bottom-up physics view, is dissect the negative capacitance mechanism, including the important subtlety of transition versus quasi-static operation, detail the auto-homologic static operation, detail like phase requirement I mentioned earlier, and critically weighs the stability, hysteresis, and speed limitation. Its strength is the why and how. Limitation, its strengths, the why and how. Reading them together gives a complete balanced picture. Paper A tells me why the industry care, and paper B tells me whether the physics will actually deliver. So let's go to the next slide. Pulling the analysis together, here's the balanced verdict. On the advantage side, the NCFET breaks the Boltzmann's limit with sub 60 switching. It enables lower supply voltage and therefore substantial dynamic power saving. It's CMOS compatible through HCO, so it can write on existing FinFET and get all-round platform. And as a bonus, the very same ferroelectric enable non-volatile FET memory, which is strategically attractive on the challenge side, which I won't gloss over. Hysteresis must be suppressed for clean logic operation. The long-term endurance and reliability of the ferroelectronics are still being proven. The capacitance matching window is narrow and sensitive to process variation, and as noted, the steep swing is frequently limited to a portion of the current stage. They are engineering challenge, not fundamental roadblocks, and that distinction is what makes the device so promising. So where the technology heading? I see three concrete directions. First, ultra low power logic, particularly edge IoT and mobile chips, where every millivolt shave off the supply voltage translate into longer battery life. Second, embedded memory, because the very same HCO ferroelectric can be operated as a FET. The technology offer dense, non-volatile, low energy memory using the same material stack, a 2-for-1 that industry find very attractive. Third, integration onto gate all-around nanosheet transistor, riding the mainstream roadmap at the 2 nanometer node and beyond. The bottom line, and my key takeaway is the NC FET is one of the most industrially credible beyond CMOS candidates, precisely because it's like augments silicon CMOS rather than trying to replace it wholesale. To conclude and summarize the whole presentation in 4 points. First, the NC FET works by inserting a ferroelectric SZO layer into the gate state, creating a negative capacitance that internally amplifies the gate voltage. Second, the amplification drives the body factor below 1, which let the device switch below the 60 milliwatts per decades Boltzmann limit, and that is the single defining advantage. Third, synthesizing my two sources, paper A confirmed the device and roadmap value from an industry perspective, while paper B confirmed the underlying physics in genuine but currently hysteresis limit. And fourth, because it's CMOS comparable, it's dual use, serving both logic and non-volatile memory, and the NC FET stands out as one of the most credible beyond CMOS candidates on the horizon. So that's all from my side. Thanks. And finally, this is my reference. So the two primary papers is analysis Khan, Kavarsky, and data. And the second one is like Hoffman and Mikolajic. And that's all. Thank you.